Okay, so we're in business. So here's where y'all left off from watching the recordings. Thanks for y'all's flexibility yesterday or Wednesday. I couldn't make it. So let's see an example here of this theorem that we ended with, that y'all ended with last time. And just a quick reminder what this theorem says. If you're interested in the question of whether or not a vector field is a gradient, let me phrase that a little bit differently. If you're interested in the question of whether a vector field has an anti-gradient, right? Because that anti-gradient, that's what you're going to use when you're using the fundamental theorem of line integrals. Right? You can answer that question just by looking and seeing whether the curl is the zero vector. Right? So, okay, well that's easy enough, and in this example, that's exactly what we're going to do. We're going to take this vector field, we're going to compute the curl, and the curl has 3 coordinates. Now, of course, this is a 3-dimensional vector. It is an unfortunate thing that the word curl gets used to describe the scalar-valued operator in 2 dimensions and also the vector-valued operator that we use in 3 dimensions. Anyway, it is what it is. So we start computing the curl, but then we remember, wait a minute, I only need to know whether or not it is 0. I don't actually need to know what it is. I just need to know if it's 0 or not. And when you're computing something, only with the need to know whether it is 0, as soon as you get a non-zero coordinate, game over, right? So there's no way that's... because that is not 0, there is no way that is going to be the 0 vector, right? So we don't even have to compute the second and third coordinates. It's definitely not the 0 vector, and that means that it does not have an anti-gradient. So don't try to find one. There is no anti-gradient to find. Okay. All right. Second example. Now this is a 2-dimensional example, so let's remind ourselves, and you can see that right here, 2-dimensional vector field. If you want to decide if a 2-dimensional vector field is a gradient, you use this 2-dimensional theorem, right? R2. And there, the test for whether your vector field is a gradient, aka has an anti-gradient, is to compute the scalar-valued curl and see if that is equal to 0. So again, it's just a plug and chug, and you can compute this curl. By that formula, you get 2, which is not 0. So there is not going to be an anti-gradient. That makes sense to everybody? Everybody happy? Okay. All right, so let's see. Here's a different point of view on this. This is just sort of for, I'm going to say, geometric satisfaction purposes. Let's not forget that we know what this thing looks like, right? That's what that vector field looks like. We've seen it before. And let's just play a game. Hypothetically, if that were a gradient, and again, hypothetically, this is what if this were a gradient. Well, keep in mind, gradients point uphill. Right? So that would suggest that is pointing uphill, and likewise that, and all of these vectors are uphill, and this is all uphill. And that would suggest that as you start walking here and go all the way around and come back, that you were walking uphill the whole way. Well, that's nonsense. Right? There's the old joke about... everybody's grandparents, or in y'all's case, his great-grandparents, perhaps. I had to walk to school, and it was uphill both ways, right? That's the old joke. No, it wasn't, Grandpa. There is no way. That's not how that works. So there's no way that this could be a gradient, because there's no way that can be uphill the whole way around this curve. Okay. All right. Moving along. So, this strategic diagram, this is a weird conversation that I want to have with y'all. There is a point of view on all of this material that is extremely powerful, extremely useful, and unfortunately quite sophisticated. And so we can't really do that, right? I can't tell you the whole story of differential forms and chain complexes and co-chain complexes. It's not appropriate for this class. What I can do, and I think this is a really valuable sort of point of view to take when you're learning multivariable calculus, is take some of those ideas and kind of boil off all the mathematical formalism and the rigor and abstraction and stuff like that. And just kind of, so what I feel like results when you do that is what I like to call just a diagram, right? And so this is not, don't think of this as a formal mathematical statement, but think of this as kind of a framework, kind of a, think about certain objects and certain operators as being in certain places, and if you do, magically, things will just fit together in wonderfully convenient, consistent ways where crazy patterns will start showing up. And analogies will reveal themselves. Patterns will reveal themselves. And it's a super convenient way to think about all this stuff. So that's what I've got here. And let's see here. We will start by reminding ourselves that we've actually seen this little short part of the diagram here before. This is from Chapter 3. And I wrote down a version of this. I think I wrote the three-dimensional version of this in Chapter 3. And that's where we first saw divergence and curl. Without much context, I made these baseless assertions about what divergence and curl do with the promise that we would make sense out of it later. Right? Okay. So this is the two-dimensional version of the diagram, and I claim the same thing, that if you take the gradient operator that turns functions into vector fields and the curl operator that turns vector fields into real-valued functions, and you compose them like this, that this resulting sequence is what you can call exact. And the easy way, the sort of the convenient, relatable take on this is that everything has a lifetime of 2. Y'all remember that business about lifetimes of 2? Yeah. Okay. So, for example, and again, being deliberately sloppy, if you have a function, and if you compute the gradient to get a vector field, that vector field, its curl will be 0. So, birth, survival, death, 0. Okay. All right. And furthermore, if you have a vector field, if you compute its curl and you get 0, there has to be an anti-gradient. That's the theorem we were just talking about, of course, right? But from a lifetimes point of view, the reason that there has to be is that if there were no anti-gradient, if there were no function whose gradient is that vector field, then that would suggest then that this is where the vector field was born, and then it immediately dies, right? And that would be a lifetime of 1, and that's not how it works, right? Everything has a lifetime of 2. With the exception of constants on the constant valued functions on the far left, and that's the one little counterexample. And listen, and I'm going to get bogged down in the weeds. Okay. All right. So stuff like that. Neat facts. Now, just for convenience, I'm going to switch over now to this other version of the diagram. It's basically the same diagram. But this is a little bit more expanded, a little bit easier to kind of draw on. By the way, this PDF file that I'm going to be marking up here it's available on the website, and I forgot to check between classes, but it's either in the course materials folder or the class materials folder. I don't remember. I'm tempted to say it's in the class materials folder, but anyway, it's available one or the other if you want to have a copy, which I strongly encourage. Anyway, here's the same little diagram. Right. And let me talk about the second line. The second line motivates from the third line. These are what I'm going to call different ways that we can evaluate these things in these dimensions. And so let's just think through. And again, I'm boiling out the formalism, right? And this is just my way of kind of justifying what is actually justified much better in very different ways. So if you wanted to do a two-dimensional integral of a function, that's what it would be. And the domain for that is a two-dimensional region. Okay. If you wanted to do a one-dimensional integral of a vector field, well, that's what that would be. It's vector line integral. That's our one-dimensional integral of a vector field. And the domain is a curve. It's an oriented curve, to be blunt. And then, okay, now the next one is a little weird. This is not an integral. There's a point of view that you can take, a very sort of exceptional, sort of weird case of a broad generalization, thinking about integrals, that you could call this an integral in a weird way, and again, not our issue right now. But notice this evaluates functions at points. Okay, so if you look at this diagram, where we take boundaries to turn one into the previous. Notice the arrows go the other way. Right? Regions, two-dimensional regions, have boundaries that are curves. Curves in general have boundaries that are points, right? Starting point, ending point. And this too is exact. Asterisk, there's a counterexample, little issues, micro problems that are not going to concern us. But if you think about it, if you have a two-dimensional region, if you take its boundary, that curve will start and end at the same point, or said differently, it never starts or ends. It doesn't have a boundary, right? It never stops, it never starts. Does that make sense? Just think about the geometry, right? Yeah.
Wait, could you repeat that?
Yeah. Okay, so if you have a two-dimensional region, such as, let's say, something like this, that's our two-dimensional region. Now let's talk about the boundary. The boundary is going to be a curve, which, in fact, in this case is kind of like this. There's that boundary curve. Now let's ask, where are the endpoints of that curve? There are none. Right? Or if you want to, you could say, I suppose, that it starts at that point and ends at the exact same point, and effectively they kind of cancel each other.
Mm-hmm. And is it by the fact that it's a closed surface? Or
It's a closed curve.
Okay.
Yeah, exactly. Right. Okay, so a little curiosity. There's a sort of an exactness here as well, and that's cute. Okay, so let me go back to here and remind myself. Oh yeah, of course. Okay, so the next thing I want to. Wrong document. Next thing I want to point out on this diagram is how our accumulation theorems appear on this diagram. And this is a really surprising analogy. I'm going to say this works much better than one would think. Right? Now you've probably noticed that the fundamental theorem of line integrals and Green's theorem do kind of have something in common in some ways, depending on how you look at it. Right? They both involve some sort of an integral computing some sort of an accumulated quantity, but they're pretty different. One's about change, one's about circulation. The geometry is really quite different. Right? Okay, here's how they show up on the diagram. Starting with Green's theorem, if you have a vector field and you compute curl. Oh, I should mention, I'm sorry, by the way, I forgot to mention, just a quick reminder, don't forget, I used to write curl as GRN, as an abbreviation of Green's operator. When I wrote this diagram, that was my norm at the time. But anyway, so we're calling it curl now, and so whenever you see GRN, that just means curl. So just read this as curl. Okay, so if you have a vector field and you compute curl, if you have a two-dimensional region and you look at its boundary, and if you do a vector line integral of your original vector field around that boundary curve like so, and if you also do a double integral of curl that you just computed over your original two-dimensional region, Green's theorem says you get the same thing on both sides. Okay, so what? Who cares? Let me streamline that a little bit. You compute curl, you take a boundary, you compute like so on the left, like so on the right, you get the same thing on both sides. Now let's do the same little diagram, Chase, with the fundamental theorem of line integrals. And notice how this works out. You take a gradient of your vector field, you take the boundary points, starting point and ending point, right, of your curve. If you evaluate your original function at those boundary points, like so, if you do a line integral of the gradient over your original curve, like so, you get the same thing on both sides. Again, abbreviating for sort of convenience, gradient, boundary, evaluate on the left, evaluate on the right, you get the same thing. Look at the pattern. It's bonkers analogous. They look kind of identical. If you think about everything laid out in this way, if you just follow this pattern, right? You think about gradient and curl composed like so, boundaries like this, dimensions 0, 1, 2. Make these assumptions about how you evaluate stuff. They look like the same theorem. Okay. Now, is this a coincidence? Did I craft this just so that these theorems would look alike? In other words, is this a manufactured example? And the answer turns out to be no. All of this very sophisticated, way above our level right now, ideas that I made a reference to. If you take all those sophisticated ideas and you boil it all down, this diagram is what you get. So what we're seeing here, the fact that this, sort of take on the fundamental theorem and this take on Green's theorem, the fact that they look so much alike, we are seeing little glimpses of the fact that they are, in fact, the same theorem. And there is a single theorem which, when applied to this circumstance, looks like that, and which, when applied to this circumstance, looks like that. We are seeing a super strong pattern because, in fact, we're seeing the same theorem twice. So it's not a coincidence. And again, this is really deep water. This is really sophisticated stuff. Gauss never figured this out. Right? I'm sure he was suspicious that, golly, there's got to be some way to connect these things, but he never figured it out. It involved math that didn't exist when he was trying to figure it out. Anyway, I just as a cultural point, if nothing else, I think it's really useful for you all to know that, there really is something very powerful going on here. And even if you don't know what the connection is between these theorems, just knowing that they are connected, I think, is, again, something that I feel like multivariable calculus students should know. Okay. How we doing? Everybody all right? All righty. Let's see here. So the next thing I want to talk about is certain special vector fields and how we describe their shared properties. So I want to emphasize to start off with, I am not talking about all of these vector fields. I'm talking about certain special vector fields. Specifically, certain special vector fields of which I might want to compute a vector line integral for whatever reason. Okay, so the vector fields in question are gradients. That's kind of the most direct way to think about them. Just gradients. Turns out they are the special vector fields. And as we've already seen, gradients have this other property that their curl is equal to 0. And you heard me talking about this last time, that means that they are irrotational. Right? So curl, keep in mind, is a way of measuring to what extent is the fluid overall kind of rotating. And if the amount that they're rotating is 0, then there is no element of rotational, therefore irrotational. Okay. But we also saw, I say we, y'all saw last time, that they're path independent. Now, the way I'm going to represent path independence on here, and keep in mind this is all hand wavy. This is not rigorous. Don't worry about, do I have to do it the following way? No, that's just the way I like to sort of think about things. I'm going to represent path independence as having the feature that when you have two curves that have the same boundary points, in other words, they start at the end point, they start at the same end, they start at the same starting point, they end at the same ending point. Those two line integrals of the special vector fields will always give you the same value. Right, so this is how I like to draw path independence. So what we have here is just an indication of, using the colors, green, blue, orange, three different features, three different properties that these special vector fields have. Okay, fine, whatever, who cares? Let me remind you, there is vector calculus in 3 dimensions. Starting today, we're actually going to start developing some of the ideas that will lead to 3-dimensional vector calculus theorems, such as Stokes' curl theorem and Gauss's divergence theorem. We'll be getting to this next week, right, really soon. There is a diagram. This is what you see here. It's going to take us a while to develop all of the objects here, and certainly to develop all the theorems and do various applications. We've got a lot of stuff to talk about. But this is the diagram that will end up relating all of those things. And here is a cool fact. This little diagram, this little pattern here that I observed in 2 dimensions, exact same pattern, works in 3 dimensions. And here's where it gets really weird. This exact same pattern, actually, let me, you know what, I have to do this. Let me do like so. I just want to get some more space. This exact same pattern here, if I shift over by a dimension, it still works. This is spooky. This is very surprising. I did not see this coming, certainly. I wouldn't imagine any of y'all would see this coming either. But amazingly, there is a whole new set of special vector fields that we're going to talk about when we get into this 3-dimensional stuff in Chapter 7. They are vector fields that are curls. Curls are special vector fields. They have the feature that their divergence is 0. And they also have the feature, now this is, bear with me on this. These special vector fields have the feature that when you look at 2 surfaces with the same boundary curve, those special vector fields will give you the same value of this object here that we haven't defined yet, but we will soon. It's called a surface integral, and specifically a vector surface integral. So, yeah, we got to define this. Yeah, we got to talk about why this is true. We got to define what surface independence means in the first place. But point being, when we develop these ideas, there is a whole pattern of relationships between objects that we're going to be studying soon and objects and ideas that we've been studying already. And I think this is tremendously valuable, just tremendously valuable. For example, it's going to turn out that the way that we're going to relate, and you can watch, be on the lookout for this, the way that we're going to relate path independence to curl being 0 is going to involve Stokes's curl theorem. And I'll tell you what, you could probably make an educated guess based on this pattern, just based on how this slides over. You might guess that the way that we're going to relate divergence being 0 with surface independence, you might guess it's going to have something to do with Gauss's divergence theorem, and you'll be right. The pattern's that strong. It's ridiculously strong. So anyway, that's one of the reasons that I really love this diagram, right? It's full of ideas just sitting there, right? And so anytime you have some understanding of, something that's going on in one part of the diagram, when you have some understanding of something that's going on over here, but I don't understand what's going on over here, you have the opportunity to just think by analogy. Well, this relates to that. Okay, well then by some analogous way, this must relate to that. And it works in almost every way, and there's some little asterisks, and there's little, details that have to be, dealt with. But it's a very, very strong analogy. So for your consideration, everything that I do with multivariable calculus when I'm thinking about using one of these theorems or trying to remember, wait a minute, how do you tell? Do you compute the curl and see if it's 0, or do you compute the divergence and see if it's 0? In my mind, I'm seeing this diagram. All you have to remember to effectively have use of this diagram is you have to understand which order do these operators go in, and what is the pattern of the theorems, right? And what's the pattern of the various properties? You make sure you understand a couple of patterns, and everything else follows from that. That's how I think about vector calculus, and that's how I keep everything straight. And that's why I never get confused and can't remember, wait, is it divergence or is it curl? The diagram always gives me the answer. So anyway, I hope you'll find this as useful as I do. It is something to definitely want to keep your eye on this as we go through and develop all these ideas. Okay. All right. Okay, so that's all I wanted to say about this stuff. Okay, moving along. So y'all remember, again, what y'all watched on the recordings last time, fundamental theorem of line integrals. Allows you to compute line integrals, but you do have to find that anti-gradient. You have to find the function here, the function whose gradient is the vector field that you were given. And so it's pretty important to, if you have some vector field and you want to view that as being a gradient of something, fingers crossed, we hope that works. How do you find that anti-gradient function? And the big idea goes as follows. If those are equal, then their coordinates are equal. Like so. If their coordinates are equal, if the partials of f are p, q, and r, another way to say that, same statement, is that f is the anti-partials of p, q, and r. That's just, this is the derivative of that, means the same thing as that is the antiderivative of this, right? It's the same statement, just kind of grammatically backwards. And then don't forget to add your integration constants. And, old news from way back when, you always add in integration constants because, well, they're free, right? I mean, the whole point to an antiderivative is that when you take its derivative, you get what you're supposed to. A constant will disappear when you take that derivative, so you can add it in for free. It doesn't matter, and it's perfectly good antiderivative. So the tricky part here is that, for example, let's look at this formula for our f. Right? And f, keep in mind, is what we're going to take the x partial of to get p. And here's the thing, when you do that x partial, the x partial of this term will give you the p. and the x partial of this term gives you 0. In other words, it doesn't matter because the x partial of a function that doesn't have any x's in it is going to be 0. Right? So when you're talking about partial derivatives, the integration constant isn't a constant. It's what we call a partial constant, which means it's a function. It's a function that just doesn't have any of the x's in it if you're talking about x partial. Everybody cool with that? All right. So, reminder, we need for this to equal to that, which means we need these 3 equations to be satisfied, which means effectively, equivalently, I just need for these 3 equations to be satisfied, which just means that I need to make sure that all 3 of these things are equal to each other. That's all you have to do. And I'll show you an example momentarily. But all you have to do to find an anti-gradient is find a way to make these 3 things equal to each other. If these 3 things are equal to each other, that thing that they're equal to is your anti-gradient. All right, so let's see an example of this in action. Here we go. Got a vector field here. First coordinate is our p. Take the x antipartial of that. Second coordinate is our q. We take the y antipartial of that. Third coordinate is our r. We take the z antipartial of that. That's just following the formulas from the previous page. Y'all can do those antiderivatives, I'm sure. And here's the thing. Don't forget your integration constants, right? Partial constants. And per the previous page, what we're looking for is we're looking for a way that we can view all 3 of these things as being the same thing. Now, easy mistake to make. A lot of students will look at this and say, oh yeah, they're clearly different. Check it out. They're like, look at the x squared y term. There's no x squared y term down here. So they're obviously different. We lose, can't find an anti-gradient. Game over. And that's a mistake. Because that x squared y that seems to be missing there, that could be what this is. And keep in mind, these partial constants, these can be anything that, as long as they depend only on the variables that they're allowed to depend on. This just needs to be anything whose z partial is 0. So it can be any function of x and y, and it could be x squared y. So we cannot, we do not have the ability to reject this as a loser just yet. We still might win this thing. And so here we go again. You see an xz. I see an xz. Hey, there's no xz in the second one. Oh, actually, you know what? Maybe there is. That's allowed to be xz. We could make this work. Right? And then likewise, minus yz squared, minus yz squared. I don't see the minus yz squared. Oh, well, maybe that's what that is. Perfectly okay. Well, in fact, we kind of won this game here, right? I mean, we have actually found something that's equal to all 3 of those things. It's green plus blue plus orange. This function right here is equal to all 3 of these things, and therefore it is our anti-gradient, and I think this is a healthy little exercise. I encourage you all to try the following. Actually take this function and compute its gradient. Right? Take the gradient of that thing, and you will get that original vector field. So we have found the anti-gradient. Everybody see the process? It's nicely algorithmic. You've got to be careful how you interpret things. Okay. Alrighty, let's see a two-dimensional version of this. And by the way, we're going to lose on this one. That's life. Sometimes you lose. Not every vector field is a gradient. In fact, from a certain point of view, most vector fields are not gradients. It's really quite special for a vector field to be a gradient, or said differently, to have an anti-gradient. And this one, in fact, we know does not have an anti-gradient, right? We've already looked at this one. This is the one that we drew the picture, and Grandpa lied when he said that he walked uphill in the snow both ways, all that stuff. So we know there is no anti-gradient here. So, all right, how does the game lose in such a case? And okay, well, let's play the game. First coordinate, x antipartial. Second coordinate, y antipartial. Don't forget your integration constants, right? Your partial constants. And thus begins the game. I need to find some way to choose these partial constants so that these two things are the same. Get creative. Think about what you can do. Take any function of only y that you like to put here. Any function that you like of only x to put here. And see if you can make these equal. And it's not going to work. That's a definite loser. Not possible. And if you don't believe me, try. And then you'll believe. Everybody happy? Okay. All right, so that does it for Chapter 6. And we move along now to Chapter 7. Again, starting off in sort of three-dimensional vector calculus. Let's see, I'll go ahead and do that. So various tools that we're going to have to develop. Recall when we started doing two-dimensional vector calculus, one of the first things we had to do is we had to define line integrals, right? We had to define vector line integrals. How did we define vector line integrals? We kind of needed parametric curves. Okay. Well, we're going to momentarily, not today, but Monday, we're going to want to define vector surface integrals. And to do so, we're going to need parametric surfaces. So how do we define a parametric surface? We've actually kind of already seen one or two of them here and there. We didn't use that language at the time. But this first example you might even recognize. But just a short answer, a parametric surface is a function that gives position in terms of two parameters instead of one. Right? Parametric curve gives position as a function of one parameter. Parametric surface is position as a function of two parameters. Right? So think back again, quite a while ago, we wrote this example here. If you want to describe points on a plane, one way that you can do that is start with any given point in the plane and any pair of vectors parallel to the plane, not parallel to each other. So you give me the orange, the green, and the blue, and I can use these givens, orange, green, and blue, and I can produce the purple. And it's not that hard to think about how to do that. All I'm going to do is take some appropriate multiple of V1 and some appropriate multiple of V2, and orange plus dark green plus dark blue, sure enough, will get me anywhere I need to go in the plane. Right? Is that cool? Y'all remember this construction from, I want to say, Chapter 1 at some point, somewhere in Chapter 1. So, in fact, this is a parametric plane. I don't think I used that term at the time. Whoopsie. But this is a parametric plane because we are looking at position in R3 as a function of two parameters. In this case, S and T. That's a parametric surface. All right? All right, now one little bit of bad news. My favorite way to think about parametric curves, and I push this real hard, you probably remember, and I hope you like it too, is to think of, when you're looking at a parametric curve, think of that one parameter as being time, right? If that one parameter t is time, then the parameterization literally traces the curve. And that's very helpful. That allows us to talk about the derivative of the parametric curve as being a velocity, right? And that kind of tracks with sort of physical experience and physical intuition. And that's nice and all. Really helpful point of view. We have to bail on that when you're talking about parametric surfaces, because we have two parameters, and you can't think of two different parameters both as being time, right? That's I guess maybe I shouldn't quite say you can't do it, but it's certainly not easy to do, and I think you probably confuse yourself more than help yourself if you try to take this point of view. So don't think of S and T as being time. Just think of them as being inputs that produce outputs. Okay. All right, how's everybody doing on that? Is that all right? All right, so it is time to talk about various tools for your toolbox. Remember, it's one of my favorite metaphors, and if you think back to parametric curves, I showed you various different ways that you can create parameterizations from various different sort of little tricks, approaches that apply in different circumstances. So again, tools for your toolbox. Again, my favorite one is what I'll start with, and again, it starts with the graph parameterization. The graph parameterization for surfaces is very, very similar to the graph parameterization for curves. If you are looking at a graph, right, so very importantly, you got to be able to solve for one of the variables as a function of the others. That's the condition, non-negotiable. One of the variables needs to be a function of the others. If that's the case, let your input variables be your parameters, and then just let it all work itself out. And it'll work itself out. So, as follows, you'll notice that this example here, we've got z is x squared plus y squared. So, z is a function of x and y. So, indeed, this is a graph. Indeed, x and y are our input variables. And as suggested here, I'm going to let x and y be s and t in my developing parameterization. And I claim we've already won. It's all over. We just, have to kind of, we've got to run it into the end zone here. But we've already won, because if x and y are s and t, plug that into there, and then z has to be that, and we win. We have position. Now let me do it like this. We have position as functions of two parameters, s and t. That's a parametric surface. Is that cool? All right. Okay, now, does it have to be z being a function of x and y? No, of course not, right? There's nothing magic about letters of the alphabet or alphabetical order or whatever, as long as any one variable is a function of the other two. So an easy, quickie example, if y is a function of x and z, cool. Just let those variables be your parameters. And so, for example, here in this given equation, well, let me go ahead and do this. If you look at this equation right here, it's not given as a graph, but it is a graph. You just have to manipulate things around a little bit. You have to actually solve for y, but it is perfectly doable to solve for y. And y is that function of x and z. Everybody see that? Okay. So yeah, sometimes you got to move things around a little bit. But that said, now that I have it written as a graph, just like it's given here, now I'm going to follow the instructions. It says let my inputs be my parameters. So x and z are my inputs. I'm going to let x and z be my parameters. Notice, again, I go ahead and put that in there in my developing parameterization. X and z are s and t. I've already won. It's just a matter of letting it play itself out. Because after all, if x is s and z is t, then y has to be that, and we win. Everybody all right? Okay, what if we're not doing rectangular coordinates? What if we're in some other coordinate system? Well, you can still do it. It's surprisingly versatile. Now, there is an asterisk. When you say a parametric curve or parametric surface, it is always the understanding that you have to solve for position in rectangular coordinates. That is part of the deal. Parameterization means in rectangular coordinates. Right? But still, if you have solved for, let's say, a spherical coordinate in terms of the other spherical coordinates, it still works. The only little extra is you do have to just, start by writing down the, your regular conversion formulas. These are your spherical to rectangular conversion formulas. Write that down first. And then, again, it just kind of works itself out. If rho is cosine phi, wrong color. If rho is cosine phi, you plug that in and we win. Because again, we have position now as a function of two parameters, and just now our parameters are phi and theta. Everybody all right? Gotta love graph parameterizations. Okay, all right. Believe it or not, we're going to have time to do what we're going to do with this last example. Because this last example, you are absolved. We're going to remove this from the course. This isn't in the book anyway. I think this is a cool supplemental example, but we're behind schedule. This is really not necessary. It's kind of a niche application. For whatever it's worth, I'll just say real quick, y'all remember way back in Chapter 1, we talked about the bicycle wheel with the reflector? Y'all remember that? And bicycle wheel reflectors make this herky-jerky kind of scallopy sort of pattern. And we can parameterize that by using vector algebra. This is using the same kind of vector addition, vector algebra approach, but it just doesn't come up as often. It's just not that useful. So y'all are absolved of that, and we will draw the line right here. And see y'all later. Have a good weekend, and I'll see you on Monday. And don't forget about attendance.